So our presenter tonight is Ben Healy. Ben's an engineer and naval architect. He's the managing director of Thrust Maritime, a company down here in Melbourne, for those of you who aren't from here. His background includes significant experience in subsea operations from the practical project management and engineering aspects. Notably, he's led the development of a fleet of high integrity launch and recovery systems from 2019 through to 2021. Ben was also a key member of the team drafting the new IMO global diving regulations. Ben studied engineering at the Australian Maritime College, business at Monash University, and in earlier days graduated from the Royal Military College Duntroon. Ben served in the Australian Army for over 20 years and is a specialist in long-range waterborne surveillance. So without further ado, I'm going to hand over to Ben for his presentation.
Thanks, Tom. Hopefully you can see my screen. Tom, just comms check. Can you hear me and see the screen?
That's all good.
Brilliant. So g'day team. Today I'm going to talk about basically our portable active heave compensation system that we've developed over the last few years. And a quick bit of background on Thrust Maritime. We, over the last 10 years, have developed a number of large A-frame systems for recovering hyperbaric lifeboats. We've got a manufacturing capability, 2,000 square metre factory in Pakenham, significant engineering capability, and all of that allows us to do subsea operations, winching, A-frames, and you can see there in the active heave compensated system, which we'll talk about today. So in this presentation, I'll essentially jump through, talk about heave compensation systems, then talk about the design, this particular product, how we manufactured it, factory testing and field testing. I'll try and keep it marketing light, but technical, try and share as much technical juice as I can. So firstly, what is active heave compensation? Active heave compensation is where a winch pays out or in really quickly in order to keep an object static with relationship to the sea floor. So if you don't have active heave compensation, an object that's on a hook over a crane or A-frame will go up and down and essentially hit anything in its path. So if you're doing operations near the seabed, it would hit subsea structures. What this means is that when you're doing fine positioning or landing out of or recovery of subsea structures or equipment, you basically need to have active heave compensation to do that effectively. There are multiple types of heave compensation. You can have passive and you can have passive heave compensation, but passive heave compensation is not as effective. Passive heave compensation essentially relies on no input of additional energy, whereas this active heave compensation we talk about requires the injection of
sorry, Ben, excuse me, sorry, your microphone was just playing up there.
Just let me check my. Okay. Yeah, so essentially it's about active heave compensation.
Sorry,
where
Ben,
a lot of
Ben, sorry, it's not fixed till the same, mate. Sorry.
Sorry, Jim. Test.
Perfect. Thanks, mate.
Brilliant. All right, so hopefully that's working better now. Active heave compensation requires a lot of energy to actively inject that pay in or pay out. So when your typical active heave compensation system will have manual control, where you're able to go up and down on the winch as like any other winch. It will have active heave compensation where you're able to essentially let the system run itself. And that is taking data from a motion reference unit to detect the movement of the vessel and then compensate or go in and out on the winch. Other modes are constant tension, where it is essentially taking data from a load cell, and that data is not working in an active heave compensation sense, but what it is doing is ensuring that the winch doesn't exceed a set tension value. And that's a useful feature for when you're lifting something off a seabed. So if something's stuck in mud or stuck to the seabed, you may want to use constant tension. Constant torque is similar to constant tension, however, it essentially uses the data input from the motor, and thus it's not quite as good as constant tension, but it is still effective. And then hybrid is a combination of active heave compensation, where you're using a motion reference unit, a sensor to detect the motion, and then you're also using constant tension or constant torque. So the benefit of hybrid is that you can lift something off the seabed and ensure you don't overload the system, but it also allows that use of active heave compensation. And it's also very beneficial for instance, crossing through the splash zone or something like that, where you're wanting to ensure that you don't have a slack line event. So as with constant tension, you can essentially set it so that you come in on any slack line event, and which is a riser to an incident. This is a bit of an image of our control station, and what you can see on the right there is what we've called EMOS, which is electronic manual override protection system. So it's a safety function, which we'll talk about later. So why did we, essentially what we're talking about is an active heave compensation system that we built, and why, what is the need for a portable system? And really the need of active heave is to maximize the sea state in which you can launch or recover something from the seabed. And we wanted to develop a portable system to enhance vessel capability. And the reason for that is that it allows either local vessels or cheaper vessels to have an increased capability and net cost savings. So we can put this system on a much smaller vessel or a local vessel and do the same job that you would have done with a much larger construction vessel. This same capability is incredibly useful for submarine rescue systems, and that's an area where we've been doing quite a bit of work over the years. And then one of the other drivers for us was to augment or support our A-frame rental business, in that by using an active heave compensated portable winch, we can very quickly put it onto a vessel and use both the A-frame and the AHC winch. So our design drivers were essentially to have something which is super high in portability, electric and air portable, and high capability. So we wanted to be able to outperform ROVs, or remote operated vehicles. And one of the reasons for the essentially the background behind going towards electric was that in order to achieve proper air portability, typical active heave compensated systems have historically been hydraulic, and the challenge with hydraulic systems is that you need large hydraulic accumulators, and hydraulic accumulators don't really travel that well, or it's difficult to get them on commercial air freight, and that was one of the drivers behind trying to making the whole system electric. So we started off the project with essentially developing a basis of design and wanting to outperform ROV operations. And we were targeting a conservative design, knowing that this was something that, you know, as a business, we were very much in the learning phase of. So we selected a 36-metre monohull and selected 3.75 metre significant wave height, an 8-second period. We based that on looking at a lot of different data and so forth. And we wanted to make sure that we were able to then put that onto a broad range of vessels. So what we did was we obviously selected sea spectrums, modelled the vessel, took the RAOs, and then used Orcaflex to develop or to look at a number of different combinations, permutations of heading and sea state, etc. In the end, we settled on a line speed of 1.8 metres per second, an acceleration of 1 metre per second as being our governing basis of design. And when you, over on the right, you can see that if you would say that the red line essentially represents typical ROV deployment capability, and you can see that the vertical axis is significant wave height and the horizontal axis is period. You can see that for 100%, essentially we're, with the winch, we're well and truly able to exceed ROV operability deployment capability. And then obviously as the significant wave height increases, our performance, or the system's performance, reduces. Yeah, and then on this plot, the colour basically represents wave occurrence in Eastern Bass Strait. So we sort of overlaid that as colour representation to get a feel for what that actually meant in waters we're familiar with. So design development. Initially we thought, oh, this is going to be easy. Turned out it wasn't. So this was the first concept, and as you can see, the winch was pretty well formed, but all of the other ancillary support systems were very ill formed. And we then did some further engineering on that, came up with some sketches and so forth, and then developed across to the right, where we had, you know, all of our main components, but we weren't fitting in one skid, and hence wasn't as portable as we wanted. Eventually, we ended up with the final down at the bottom. But I guess what this slide demonstrates is that it's such a system requires a lot of multiple subsystems, such as cooling, you know, electrical drives, etc., hydraulic, you know, protection systems, and you know, it's amazing to see that the difference from the initial concept. We grossly underestimated the complexity, but in the end we got there. So what did we end up with? We ended up with 13.5 ton skid that fits inside a 20-foot high cube container for storage. We designed it to DNV GLST0378, which is the offshore and platform lifting appliances code from DNV. Fully electric with, we went for an ultra low inertia motor. So one of the drivers was to obviously meet the basis of design from an acceleration perspective. And in order to do that, we went for the, you know, quite a special motor to achieve that outcome. It's operated from an integrated control stand. So essentially the whole thing, we wanted to make sure that it could be operated from a single lift onto a vessel, and away it would go. And then we've also added a remote pendant, allowing local control for the splash zone crossing. This plot up on the right essentially shows that at 400 metre water depth, we can the system can provide a 12-ton safe working load capacity, but then we can change out the shells on the drum and provide a smaller diameter rope, and then basically go down to 1,100 meters water depth, but with a reduced safe working load. So these are a few photos. It's essentially, we've got an electric spooler, which goes back and forth in sync with the drum layers. Electrical switchboard. The drum has a lever style grooved winch, so that allows us to basically put more layers onto the drum, and is a special way of grooving the drums. And then essentially it's got dual automatic fail-safe brakes. You can see here that we've designed it for rapid sea fastening to deck. So essentially there's numerous bolt interfaces so that we can bolt on some gusset plates and then weld to deck. It's also got ROV video feed, so essentially a duplication monitor, and then the control station, state indicators, and a manual override protection system. So this is a hydraulic system, which we'll talk about later, but it is for use in the event that everything else fails. So looking at the end, essentially there's electrical switchboard, numerous electrical drives, and essentially a cooling system. The electric motor has glycol, because it's quite a special low inertia motor. It has glycol fed through the actual motor to keep it cool. And obviously that glycol then needs further cooling as well. Breaker resistor, and this is the cooling fan system. The actual winch itself has obviously a gearbox, and that's a planetary gearbox which actually sits inside the drum. And for that gearbox, it needs cooling as well, which is this cooler up here. And then for this sort of operation, you want to have a reasonable amount of redundancy. So you want to make sure that if your power supply fails, you've got immediate backup power supply. So essentially, we made a immediate changeover box so that we can change to an alternate power supply or alternate generator or ship power supply. And then your basics of forklift time pockets. So at peak power draws 280 kilowatts. Typically, we use a 350 kilowatt kVA genset, and yeah, we've got essential ROV feed onto a monitor at the control station. And it's from an installation perspective, it's quite simple to install. It's a single lift on and then connect it up. And from a calibration perspective, many other hydraulic systems and so forth require calibration of hydraulic accumulators, whereas with this system and the ability for, or like an electric drive system, one of the beauties is that it doesn't require, or it requires very simple calibration. Essentially, you need to know the location of the last sheave, location of the winch, and the vessel center of gravity. And they're the key inputs into your motion reference unit, which then drives all of your sensors and so forth. Yeah, let me see. So the system works with, for constant tension. There is a load pin which we have that works with the system, so that can go into an A-frame or into a sheave or any sort of sheathing arrangement, and that's used for the CT, but it doesn't need to be used. So you can, if you don't use the load, that load cell pin, you can use the constant torque instead of the constant tension. It can be used, the whole system as a whole can be used with a sky hook. So you can reeve it through a crane or an A-frame or any other high point, or indeed you can just go straight over the side of the vessel. One of the drivers was to make it so that many a vessel that it will go on will have deck timbers and vessel T-bars that run transversely to keep those deck timbers in place. So that was quite a driver for the design of the structure of the base, that we could interface directly into those deck timbers and essentially ride over the top of those deck timbers. So some example layouts, it's designed to be able to go either over the side or over the stern of the vessel. So you can run it over the stern or over the side like that. And you can see here that this is one of our smaller A-frames that we used in testing. And the AHC winch there that essentially we ran over the top. I'll show you a video in a minute. So typically we'll store it at the location of its last job. And we designed it so that it could fit inside a 20-foot high-cube container for maximum weather protection, but we've also made a tarpaulin for it. Essentially, we wanted to make it easy to go, on a standard shipping container anywhere around the world. So this is a functional block diagram, getting into a bit more detail. So you can see on the left, typically we'd have two generators supplying the winch skid, and this dotted line depicts the extent of the winch skid. This dotted line up here is a hydraulic power unit, which would typically be another mobile unit, which would be driving an A-frame or similar, crane or overboarding device. And we've got a backup system from that HPU, which allows us to use a backup hydraulic motor in the event that we lose complete power failure. There's complete power or control failure on the AHC system. So these primary power comes in, goes to a switchboard, goes to the active heave compensated console, and that's also able to be controlled by the remote pendant. From the switchboard, it also goes to a variable frequency drive, which drives the motor of the winch. The thing is that's fine to drive it in one way, but when you're going up and down very rapidly, what happens is you have a lot of energy being injected into the winch, but then you have a lot of return energy. And that energy that is returned needs to be burnt off. And so that burnt off energy goes into a braking resistor, and that's where a lot of heat is generated. So essentially this motor is going maximum pace in one direction, 6 or 7 or 8 seconds later, stopping and going maximum speed in the other direction. So it's quite an unusual load case for a motor like that. From the switchboard, we've got a variable frequency drive going into a motor for the power spooler, which doesn't need to be used, but what it means is the winch can be closer to the last sheave. And then from the switchboard again through to a brake hydraulic power unit and cooling system more generally. Typically, when you're using this winch, you'll have an ROV system on board as well, remote operated vehicle, and that will have its own generators, or you can couple the generators, but you'll have a video link going from the video and audio link going from the ROV shack or control container into the switchboard, which goes into the operator console. And then the ROV essentially working with the load, undoing connection points, subsea or whatever it may be. So one of the challenges for this system was working through the failure modes and making sure that we had sufficiently robust failure methodologies. So the first failure mode is fairly straightforward, which is just a single power failure. So essentially what we developed there was a uninterruptible power supply, or UPS, which maintains the control system for 10 minutes and then allows you to manually change over the power to the alternate power supply. So that's fairly straightforward. The next one was more challenging, and that was complete system failure. So what we wanted to ensure that was that if there was some random event that caused complete system failure, we would still have a way of recovering the load. So the last thing we'd want to be stuck with is a load halfway subsea, or hanging on the hook over the side. So what we developed was a system where the motor can be removed from the winch, and a hydraulic drive can basically be placed in that position of the motor. So we did multiple trials of that, and so talking about this motor here pulled out. So we basically made a mini gantry system allowing that motor to be pulled out at sea, and a hydraulic motor to be inserted into the winch at sea, and did multiple tests of that system. So that was quite challenging to develop. And the next one was inventive DP runoff, so dynamic positioning, a failure of the ship's dynamic positioning system. So there's a requirement to have a manual overload protection system, and this is used in the event that the equipment that you're lifting is connected to the seabed. So what we needed to generate was an electric manual override or overload protection system, which worked in unison with the UPS and the control system, which was quite a challenge. The next failure mode was wire rope failure. Essentially, what we did there was made a protected cage for the operator. And then the last one was a combination failure, where in the event that you have a DP runoff and any other failure. So essentially what we developed there was a manual hydraulic pump system. And you can see that's all of this system here, where you can use, you basically connect in some levers to these hand pumps and pump the brakes off the winch, and that allows the winch to pay out, which would be a last case event, but it would be absolutely necessary if you were connected to the seabed and you had a DP runoff, which is plausible. So we wanted to manufacture the whole winch in Australia, which we did, and essentially develop our supply chains with Australian local content, or 100% in Australia, which we did. So this is a photo on the left of the steel plate, which was cut and then rolled to make the drum, and then the whole drum and drum frame was machined. And then, so you can see the drum up on the top left there. And on top of the drum, we have these shells, and these shells are really beneficial, because what they allow us to do is to change out the wire rope and operate at different water depths with different load ratings. It gives us flexibility in that respect. So they were machined in New South Wales and then fitted to the drum. They're quite a special machine. The actual grooving is quite special, in that it is typically called lever grooving, but that allows many more layers to be added to a winch drum. And then this is the manufacture of the actual winch frame, which was done in-house and then load tested up on the right. So you can see this photo shows some of the electrics and control systems and so forth. A lot of complexity involved in it, and you'll see in the coming slides the testing regime that we went through to sort of build up to the final product. The final product has covers and so forth over most of this cabling, but as you can see, there's heaps of different PLC or subcomponents within the electrical switchboard. This up on the top right is the gearbox cooler. Yeah, talked about that. So testing involved hardware in the loop for essentially the prototype or for prototyping of the system. So we needed to develop the software code base, and also just the there was also a lot of mechanical testing to be done. So one of the challenges with testing is that it involves a significant increase in risk. And what we needed to do there was a lot of risk management. This being the first time we'd done such a complicated build or design, really detailed task plans, which were difficult and time consuming as we were trying to learn. And throw on top of that, we had COVID. So as in working in a COVID environment was challenging. Common is regards reverse AHC. So when you're doing testing of an active heave compensated system onshore, it's essentially the opposite of doing it on a ship, because normally the ship is moving and that's your test platform. Whereas onshore, you need to inject or input somehow a signal to simulate the movement of a ship, which in itself generates quite a number of challenges, because the whole the loads are different. The whole gravitational effect is different. So that was a challenge for testing. So this is some of the testing in the factory. Before we fitted everything out, we wanted to make sure that it all worked. And we set up all of the drives on a workbench, set up the switchboard. We made a dummy winch and motor and so forth. This is Gary, our principal electrical engineer. And then we connected that, all of that up with a cooling system and essentially set everything out in the factory. And what that allowed us to do was to run through all of the modes and functions and get our heads around the whole control system. What we also then did was on the left, you can see here a tower. And essentially we set up this dummy drum with a wire rope going through a sheave and down to a weight. Then we had a vertical post, and on that post we put the motion reference unit, which is the sensor which tells the system the movement of the ship. And then we drove that motion reference unit up and down, and that allowed us to essentially inject a simulated wave signal into the platform that was supporting the motion reference unit, and then have the motion reference unit do the data acquisition, and then drive that or feed that data into the winch system and go from there. So what you'll see here on the right-hand screen, that's the motion reference unit, and it will go up and down. And then the motion reference unit is being driven by a simulated signal, but it's generating its own signal, so it's completely independent of the signal that's being input into it. And then using that signal, we're essentially compensating for the heave. So this was early factory testing. So you can imagine when we first got this going, it looks so simple now, but by golly, there was a lot of cheering in the team. Yeah, so essentially it's it was the first working AHC model. So we then progressed from that model through to a number of other tests. So one of the tests was to allow us to ensure that the motion reference, so in this vertical testing, that really only deals with heave. It doesn't deal with roll and pitch, which in order to deal with roll and pitch, we made a seesaw arrangement, which allowed us to put in extrapolated or different values of essentially X and Y, and allow transposition or extrapolation of the motion, allowing us to put the winch in different locations on a ship. So that was quite a testing sequence that we went through, testing, learning, developing, redoing. And then we had to do essentially to make sure that the spooling of the winch was correct, numerous spoolings on and off, and similar type spooling tests with, it's not shown on this photo, but with the electric spooler that runs back and forth, which is really important if you want to reduce your distance from the winch to a sheave. So lots of challenges there. From the sort of inside the factory, we progressed to outside, and we set up the winch over a launch and recovery system, small A-frame we had, and set guidelines from the concrete to the top of the A-frame, and then essentially tested with up to 10 tonne outside, using again the simulated motion input. So we were testing both straight sinusoidal waveforms and also simulated waveforms from Orcaflex, so multi-directional and yeah, which generates its own challenges. So this was the setup, a bunch of counterweights to hold the whole skip down, operating platform, and yeah, it really allowed us to improve our operational procedures and refine, you know, the whole system. And what it was also necessary for was to test our sort of states and modes. When you've got 10 tonne or, you know, with these sorts of loads, it's quite a scary amount of load. So what we did was we built up to those loads progressively, going through the different states and modes, manual control, active heave comp, CT, and so forth, and with different tests to do that, to build up confidence in the whole system. You know, at the same time, considering cooling and so forth of the system. So I'll just turn the sound down there a little bit. So this is a video of some of the testing. So this is a regular waveform, just going up and down with a simulated signal. Again, it may not look like much on a video, but it's a hell of a lot of load. And yeah, indeed, you know, we had challenges such as wind pushing the load around. That was where the requirement or the thought was to have the guidelines to prevent the wind pushing the load around. Yeah. So the next step was to go to sea trial, and we did sea trials down to 400 meters depth. essentially we chartered a vessel and put the winch on the vessel. You can see tool container, number of dummy weights, and a generator, which you can't see, but you can see in the GA there. So again, we wanted to test all modes, states, functions, and test the whole system live. So this was quite a peak of COVID and in Victoria. And what that meant was that many of us actually hadn't been within close proximity of each other. So there was a whole challenge to get actually onto a vessel. At the time, we were restricted to being within 5 kilometres of home and not going to work. So it was quite an excitement to go onto the vessel. And one of our key team members, Keegan, had a big birthday on board. So it was really quite a fun and enjoyable time. One of the first things we did when we installed the system was a load test up to 19 tonnes with these water bags. And this is us on the way home. Happy days. So we used an ROV to essentially to see the load on the seabed, and that allowed us to have actual verification with reference to the seabed. So it was a very lightweight, small ROV, but it did the job. Down to 400 metres, pretty damn impressive. So this is just the deployment of the ROV. It's amazing how far ROVs have come in the last few years. Previously, this would have been a massive, ginormous hydraulic pipe system, but now it's hand carry, electric, battery. Indeed, it's battery operated with control via or power supply via. Sorry, it's battery operated with control and video via fibre optic. Pretty impressive. So sea trial summary, we did 2 test periods that totaled 6 days at sea in very varying conditions. The video you see there is pretty calm, but we certainly had some challenging conditions. Validated all states and modes. Performance was bloody good. It exceeded our expectations. And some of the lessons learned for sea trials were that detailed planning is really critical, and contingency planning with that planning is really important too. The other thing was that cross-training of roles was critical. So we had a number of the team fall ill with seasickness. Indeed, day one was a horrific day offshore. And so a lot of the team hadn't been to sea for a while, and some of the team had never been to sea. So obviously the seasickness tablets help a lot. And what we identified also after the first trip was that onshore support for data processing. So we were doing a lot of data processing to verify the performance of the actual system and to run through all of the tests and so forth. So that was really important for us. So this is a video.
Active heave compensation is where the winch detects movement or heave of the ship, and it winds in or out really quickly in order to keep the hook static with relationship to the seabed. It's typically used for launch or recovery of specialist equipment that you would want on the seabed. Things like subsea control modules, chokes, valves, special pipe work. It's also really helpful for decommissioning projects because you can do the whole project more efficiently from a cost perspective and operational time perspective. We'd use this particular winch because it'll save you money. You can put this winch onto a local vessel, and that local vessel is likely to be cheaper than an overseas subsea construction vessel. Here we've put it on a 34-metre catamaran. It provides the same capability at a much reduced cost. What we've been doing here over the last few days is sea acceptance trials. So we've been using this 34-metre catamaran, Silver Star, to confirm that the winch that we've developed is working as planned and validating its performance. This winch is special because it's, as far as we know, the only one of its type in the world, in that it's a rental winch and also it's an electric-driven winch. The electric drive is a very low inertia electric drive. It can go in and out really quickly and provides really good performance in the active heave compensation. Its capacity is 12 tonnes in air, and it can also handle an 18-tonne dynamic load. You can do this with 450 metres of wire rope. If we adjust the configuration, which can be done quite easily, we can go to much deeper water depths, down to about 1100 metres, but that does reduce the lifting capacity. We've designed the winch to a Norwegian standard, which is DNV GL ST0378. In addition to that, we've confirmed that it complies with all Australian standards and Australian marine orders. We did the design in our Melbourne and Devonport offices, and then we manufactured the winch in Pakenham, Victoria. We're proud of that we've done it all in Australia using our in-house team, everything from the fabrication through to the programming and including the testing.
So there's another short video here. This is really showing the comparison of, this was within 20 minutes of each other. So you can see on the left, without active heave compensation, huge amount of snap loading occurring. And on the right, you know, it's holding the load almost, or holding the hook almost perfectly, or about 50 mil tolerance of the shackle there. The ROV was struggling a little bit at this point, just due to the currents and so forth, but that's why the heading is not perfect.